In this video, we address the problem of high-resolution flood modeling for heavy rain events, based on computational geometry techniques.
This morning, more than 25 million Americans across the Northeast are under flood alerts after deadly and devastating flash flooding swept through New York. Just north of New York City, parts of the Hudson Valley saw a once-in-a-millennium levels of rain.
What I've seen with this event so far are tremendous rainfall rates. Those tremendous rainfall rates are a calling card of what we're seeing with climate changing.
Am Mittag wird in Goslar der Katastrophenalarm ausgerufen. 350 Feuerwehrleute versuchen mit allen Mitteln, die historische Altstadt, UNESCO-Weltkulturerbe, gegen die Wassermassen zu sichern.
Flooding is global, and it's not just rivers rising slowly. Increasingly, it's intense rainfall that turns into destructive runoff within minutes. Where the water goes depends on countless details: terrain shape, saturated soil, streets and buildings, drainage systems, small channels, even curbs and walls that redirect flow. And even when barriers and temporary defenses are available, the key question is, where do they make the biggest difference? Because resources are limited, and placement is everything. Put a measure in the wrong location, or deploy it too late, and it may have little effect. What's needed are tools that can test many plausible scenarios quickly, so emergency planning can focus on critical points where small changes can have a major impact. Fortunately, geographic data are nowadays widely available, but to simulate flooding in large areas, we need scalable tools with sufficient performance to handle the massive volume of data. This is where Scalable comes into play. Founded in Denmark in 2010, this company develops digital tools for geographic and environmental modeling. Their technology is based on decades of basic and applied research in algorithms, data analysis, and computational geometry. This is not just engineering practice. Scalable has deep roots in computational geometry research, with the founders coming from the CG community. Scalable provides an interactive web platform for working with terrain and surface water data at scale. It offers ready-made analyses to quickly identify likely flow paths, ponding areas, and exposed locations. These analyses work with a static representation of the terrain and a given amount of rain on each terrain cell at a high resolution. And due to clever algorithm engineering, they scale to entire countries at a 1 square meter resolution. These scalable techniques are static. They do not consider the dynamic behavior of water. This makes them useful in relatively flat areas, such as the city of Braunschweig, where flood damage is mostly caused by stagnant or slow-moving water. However, in mountainous regions, such as the city of Goslar in the Harz Mountains, these restrictions make the static tools drastically less useful in predicting where problems may arise. They cannot model flow paths that can become overloaded, leading to water backing up or taking potentially destructive alternative routes. They also cannot capture the destructive potential of large amounts of quickly flowing water. Here, a dynamic model is required. At the highest level, this adds another dimension to the mix: time. For instance, in order to identify risks, we need to be able to realistically model existing streams, where a large amount of flowing water is mostly fine, and separate them from surrounding buildings and streets, where a large amount of flowing water poses a significant threat. We also cannot entirely escape the need for scalable solutions. Even if we are looking at the scale of a small city such as Goslar instead of an entire country, we may still have to model a large upstream area that drains into the city. In Goslar, for instance, we need to model an area of roughly 370 square kilometers. To model dynamic water movement across landscapes, we use hydrodynamic simulations that discretize both space and time. The spatial domain is first divided into a square grid with a resolution of 1 meter. Time then advances in discrete simulation steps. Each grid cell stores physical quantities, such as water volume and momentum, which are updated based on interactions with neighboring cells. To ensure numerical stability and accuracy, the simulation uses adaptive time stepping. If water velocities become high, a fixed time step might allow skipping neighboring cells. To prevent this, the model reduces the time step. When velocities decrease, the time step can be increased again. This dynamic adjustment balances accuracy and performance throughout the simulation. For our simulations, we use the two-flow HPC solver, which can be executed through Scalable's hydrodynamic modeling interface. The simulation requires a variety of inputs, such as the elevation model, land use data, and information about underground structures like culverts. Our setup also includes infiltration models to account for water absorption into the soil. When simulating large-scale areas, spatial resolution is a major challenge. High resolution is critical within cities, but also computationally expensive to simulate, while in less complex regions, lower resolution is sometimes sufficient. To address this, we use an adaptive grid based on a quadtree data structure. This approach dynamically refines the grid in areas of interest and coarsens it elsewhere. In our setup, important areas are simulated at 1 meter resolution. Less critical areas use coarser resolutions of 8 or 16 meters. The grid is refined around buildings, streets, culverts, and streams. In our experiments, we compared quadtree-based simulations with a uniform 1 meter resolution model. The results show that both approaches produce very similar outputs. However, the quadtree approach reduces runtime by more than 90%, demonstrating substantial computational savings. Although adaptive grids significantly reduce computational cost, they typically scale only to areas of tens of square kilometers. Our second improvement addresses scalability. We subdivide the simulation domain according to the natural flow of water by using a data structure called depression-free flow graph. It resembles a static stream network, a well-studied data structure in the literature, and can be accessed through Scalable. This allows us to extract watersheds, which represent all areas draining into a specific cell. Using these watersheds, we subdivide the overall domain into regions that can be simulated efficiently on a single machine. Because upstream regions influence downstream regions, we define interfaces between simulations. Water flowing across these interfaces is transferred using hydrographs, i.e., time series describing discharge over time at specific boundary points. This approach provides two key advantages. It enables parallelization and simulation of very large areas. It localizes adaptive time step reductions to specific subcatchments, preventing small high-velocity regions from slowing down an entire monolithic simulation. The result of our partitioning strategy is a subdivision of the area into manageable simulation units, and a dependency graph describing the relationships between them. Based on these dependencies and the number of available machines, we solve a scheduling problem to determine the optimal execution order and minimize total runtime. The runtime for each job is estimated based on its corresponding area. Our combined approach enables large-scale simulations. A uniform 1 meter simulation of the entire 370 square kilometer area is impossible because it exceeds available memory. Our first technique subdivides the region into smaller, manageable pieces with dependencies shown by the arrows. This enables simulation but would still require 21 days. Our second technique applies quadtree-based adaptive resolution to each region, using fine grids only where needed. This achieves a 7-fold speedup, reducing total runtime to just 3 days. As a demonstration, we simulated a 5-hour heavy rain event with a 100-year return period over the 370 square kilometer region around Goslar. Beyond enabling large-scale simulations, our computational capabilities unlock a second critical application: sensitivity analysis. Among other inputs, precipitation is inherently uncertain. We conducted a multifaceted sensitivity analysis, varying precipitation inputs and resolution across our study area. Here, we examined 2 simulations with the same input rainfall, but different resolutions. We successfully identified a critically unstable location, where only the left simulation shows runoff water flowing across this intersection, and the city center floods. Thus, relatively small variations in input, corresponding to the rounding errors of a coarser grid, result in huge variations in the output. While this may seem like bad news for predictability, it is indeed excellent news for mitigation efforts. Targeting this intersection promises to be particularly effective, as small interventions can make a crucial difference. While this cannot undo the great challenges of flooding and climate change, it promises improved insights into where to use our limited resources for the greatest impact. We are hopeful that this will be helpful in other locations around the world.